Alright, so in our problem, we're on a distant planet whose mass is twice that of Earth and acceleration due to gravity is 1/4 that of Earth. So, we're going to use the law of universal gravitation, but since one mass is so insignificant, we're just going to switch it to this one, where we have the mass of the Earth times the gravitational constant divided by radius squared with the force of gravity of the Earth. We're going to solve for r, and here you see I've solved for r. Now, since we have 2 me and 1/4 gravity, we're going to add an 8 right there because of algebra, and we're going to get the radius, which is 1.275 times 10 to the 7th meters. And that's part A.
So part 2 is to solve for the escape velocity, which is the velocity where a gravitational pull no longer affects an object. So in order to do that, we will be using the law of conservation of energy, which states that the kinetic energy plus the potential energy will equal 0. So the definition of potential energy is negative gravitational constant times the mass of one object times the mass of the other, all divided by the radius of one object. And for kinetic energy, we will use the equation kinetic energy equals 1/2 mv squared. So we go back to our first equation, and then we plug values in, and we set them equal to each other. So we have kinetic energy equals potential energy. So then our next step is, since they both have a mass constant, we cancel that. And then we rearrange it with algebra to get the escape velocity by itself. And that gives us this equation, which is the universal equation for escape velocity. And finally, we plug in our initial values, which were that the mass of the planet is 2 times the mass of Earth, and the radius of the planet that we got in our last problem is 1.275 times 10 to the 7th. So we plug in values, and we get 11,000 meters per second.